Well, it's 5 o'clock in Albuquerque, so I'm going to start now. Um, the topic for today is ghost contours. Um, and the idea is that one often needs to do an integral that is not a closed counterclockwise contour. In fact, that's the typical case. Integrals along the real line or the real axis, occasionally the imaginary axis, occur frequently. And one can sometimes convert a line integral into a closed contour by adding a contour on which the integration vanishes. So the picture, in fact, is as diagrammed here, or to start over again for this particular class. So the idea is ghost contours. And so here's an example, this particular integral that we've got here. It is an integral with three poles, and if we draw the two axes, then we've got a pole here at I, a pole here at 2I, and a pole here at 3I. And we're asked to integrate along the x-axis. So we're supposed to integrate here along the x-axis like this. And so what can we do? Well, the natural thing to do is to say, well, we're going to add a ghost contour, and I guess maybe I'll write it in yellow. And that's a contour on which the integral, in fact, vanishes. And this contour, the idea is that this contour is along z equal to big R e to the I theta, R going to infinity, and theta going from 0 to pi. And so that's the yellow contour, which somehow became red because my finger touched the wrong part of the screen. And the integral along that is 0 because you see it's an integral along this contour, and it's dx over x minus x, what is it? X minus I, x minus 2I, x minus 3I. So for large x, in other words, when we're way over here or way over there, the value of the integral is very, very small, and so we can add a ghost contour, and what happens then is that as we integrate, x becomes a complex variable, and we integrate, and then x has, over here, x has a large real part, up here, x has a large imaginary part, and in here it has a fairly big real and imaginary parts. Anyway, the thing is 0. I'm sorry, the thing is, the integral on the contour is 0. But the integral along the real axis, of course, is something else, and we don't know. Our task is to find what that is. Well, the clever thing to do is to add a different ghost contour, namely one that does this, one that goes around like this. This also is a ghost contour, but now, and so the integral along the blue line is 0. And so this is an integral then of an analytic function in a region of analyticity, and it's a closed contour. So this integral I equals, in fact, is 0. So that's the answer. You might say, well, that's really strange, because if we do it the first way, we pick up 3 poles. Namely, we pick up this pole, that pole, and that pole. And would they really add up to 0? Well, yes. The answer doing things that way would be, whoops. All right, I've got to undo that. Over here. The answer that way would be 2 pi I, and then the first pole would give us 1 over I minus 2I, I minus 3I. The second pole would give us 1 over 2I minus I, 2I minus 3I. Of course, this is something that can be simplified. And then the third pole would give us 3I minus I, and 3I minus 2I. That's 2I. Well, this is pretty messy writing. Let me see if I can fix that. That's an I. 3I minus 2I. And if you add them up, I'm confident that you'll get 0. On the other hand, maybe I should actually show you that explicitly. So this is 1 over minus I minus 2I plus 1 over I minus I plus 1 over 2I I. Well, what is that? This is 2 pi I. The first one is the minus signs cancel. The i's give us a -1, so this is -1/2. The next one is +1, and the one over here is -1/2. And indeed, you see we do get 0. So that's an example then of ghost contours. And obviously, when you have such a situation, what you want to do is you want to look at the integral you have to do, look at the function, figure out where it's analytic, figure out where it's big, where it's small, and then see if you can add a contour that is either 0 or easy to calculate, and which then allows you to get a closed contour. Once you have a closed contour, you can apply Cauchy's integral theorem, which is the integral of an analytic function along a closed contour in a region of analyticity with no singularity. That's 0, or Cauchy's integral formula, which is what I used here. So the Fourier transform of a Gaussian. Now, this is finally something that I promised you in the previous, in an earlier chapter 4, I think. And what is it? Well, once again, let's just consider, it's again an issue of a ghost contour. So let's think about doing an integral dz e to the minus m squared z squared. Well, that's an integral. When we're thinking of doing that, let me put in the axes. So this is the real axis, the imaginary axis, the real axis. And we're going to be going from, we're going to be integrating from minus r. So let me go in blue now. We're going to integrate from minus r along the real axis to plus r. Of course, we're letting r go to infinity. And then we go up to some point called, this would be then r comma c in Euclidean coordinates. And then we're going to integrate back this way to a point that's minus r c. And then we're going to integrate down this way. And the integral we're doing, of course, is integral dz e to the minus m squared z squared. Well, right away on these vertical lines here, these are two ghost contours of length c. And the reason they're ghost contours is that the integral, the function is essentially e to the minus m squared r squared, apart from small contributions due to the fact that that z is has some imaginary part. So these two vanish, and what one has then is that this is in fact equal to just the integral from minus r to r dz of e, well, let's just say dx, in fact. So let me undo this. Dx e to the minus m squared x squared. And then it's plus this last integral here, which is an integral from, not that one, this one actually, from r plus ic to minus r plus ic of dz e to the minus m squared z squared. On the other hand, this is an integral of an entire function. E to the minus m squared z squared is analytic everywhere. And so the sum of those two is equal to 0. And that tells us then that the integral minus r to r dx e to the minus m squared x squared is equal to the integral from the integral along this contour, which is not a ghost contour, the integral along this contour. And if we flip the sign, in other words, instead of going this way, we go that way, then it's an integral from minus r plus ic. We pick up a minus sign, in other words, to r plus ic. And we can then call it dx e to the minus m squared x plus ic squared. So that's in fact what I have here. And that then is equal to this integral, which of course is just a Gaussian integral. And that integral is a standard integral. In other words, this is just equal to square root of pi over m. And by the way, this is an integral that was done by a trick long ago. Let me get a chat window going here. I should have set one up. I should make it automatic. So why don't you write in the chat window whether you want me to tell you what the trick is for doing this integral, because just offhand it might look like hard integral, but it's just okay. So some people want me to do it. All right, so let's do that integral. Here's the trick. The integral we want well, let me stop using red. I think that's a little bit alarming. The integral we want, the square of the integral we want would be integral dx e to the minus m squared x squared, integral dy e to the minus m squared y squared. So this is just an integral over the whole complex plane. And we can rewrite that as an integral dx dy e to the minus m squared x squared plus y squared. That's over the whole complex plane. If we change now to angular coordinates, this is an integral e to the minus m squared r squared 2 pi r dr, integral from 0 to infinity. And so that is just, of course, 2 pi, an integral 0 to infinity, r dr e to the minus m squared r squared. Well, of course, what we're going to do now is let me set u equal to mr. And so then this is 2 pi over m squared integral 0 to infinity u du e to the minus u squared. And now I just find it absurd that I'm going to let v equal to u squared. And so this is equal to pi over m squared, integral 0 to infinity dv e to the minus v. And of course, that's equal to 1. So this is pi over m squared. So what do we have? The integral we want then is the square root of that. So the integral is square root of pi over m. And that's what we've gotten here. So this is that's a trick that is, it's a cute trick for doing that integral. And I think once you've seen that trick, you can, whenever if you need to do this integral and you don't have a MATLAB or Mathematica or anything handy, you can just do what I just did, which is, in fact, if you're smart, you'll do it more quickly than I did it. So this statement then is to get back to the complex variable theory. The integral from minus infinity to infinity dx e to the minus m squared. M squared, of course, has to be a big positive number, or doesn't even have to be big. It has to be positive, though. So m has to be real. X plus ic squared. This is independent of c, and it's equal to the same thing as dx e to the minus m squared x squared, and that's equal to square root of pi over m. We now plug that in to this formula. We see that, in other words, we set c equal to, where am I here? C, oh God. All right, I'm going to see if I can just erase everything. Oh my God, what has happened here? Good Christ. This is not, is this what we were doing, or is this something that I finished ages ago? Let's see where it goes. I'm sorry about this. It's this thing about these damned all right, so we're back to where we were. So let me, I'm hesitating to do, all right, let's see if I can erase this damn thing. Oh no, it won't let me do that. Oh God. All right, all right, so I'm just going to live with C equals. So what we do is we're going to set C. Oh, Jesus. Okay, so now I am going to, in fact, let me maybe get rid of this. What? What is going on here? Every time I try to do anything, it frustrates me. Let's go to red. Let's get rid of this. All right, this is just absurd. By the way, if anybody has any advice for how to deal with this iPad situation here, let me know. Type something in the chat. Anyhow, so I'm going to just use the text then for a while. We just set C equal to K over 2m squared in this expression. And what we get is this expression, namely that the integral over square root of 2 pi e to the minus I k x e to the minus m squared x squared turns out we can rewrite that as 1 over square root of 2m e to the minus k squared over m squared. So in other words, the Fourier transform of a Gaussian is then another Gaussian, and it looks like that. And so this again shows us what I said to you a few weeks ago, that if m squared is small, then this is a very broad Gaussian. So it goes nuts even if I'm not doing anything. I just touch the screen and the damn thing goes nuts. All right, I don't know what the hell to do. Okay, anyway, what we derive from this is that the Fourier transform of a Gaussian is another Gaussian. If m squared is small, then this is then e to the minus m squared x squared is a very broad Gaussian like that. But if m is small, its Fourier transform then is e to the minus k squared over m squared. M is small, so this is a very sharply peaked Gaussian. Similarly, if this m were huge, then this would be sharply peaked in x and very smooth in k. So the Fourier transform takes you from one limit to the other. And I don't know what to say. So we divide both sides by square root of 2 pi and so forth and change variables a little bit. Then we get an expression that is that comes up when one wants to do a path integral or a partition function. Coming back to this, we see that for as long as m is positive and z is an arbitrary complex number, we have this expression. Well, this sort of follows directly. So another example of ghost contours, suppose you want to do this integral, cosine of x over q squared plus x squared dx from 0 to infinity, positive q, say. Well, since this, if you let x go to minus x, the integrand doesn't change, we can just divide by 2, and then we have an integral along the whole real axis. And then we can write the cosine as e to the ix plus e to the minus ix over 2. And then we then have two integrals, a quarter e to the ix, and then we factor the denominator. Q squared plus x squared is x plus x plus IQ times x minus IQ. And so now we have again two integrals along the real axis. And so you might say, well, we've made things much worse than before. But in fact, we now promote x to a complex variable z. We can add the contour r e to the I theta to the first integral and r e to the minus I theta to the second integral. And the reason why we choose one or the other is, you see, the first term, we've got e to the I z dz over that. It is then these terms here, and this vanishes in the limit r going to infinity. And so that first integral that first contour integral is a ghost contour. And we can do a similar thing for the second contour, whereas the second contour we're doing r e to the minus I theta, and we're going to go around like that. And so now we have two different contour integrals. Now we use Cauchy's integral formula to work them out. And it'd be 2 pi I divided by 4, so that's I pi over 2. And we pick up one pole from the first integral, another pole from the second integral, and then we combine them, and we just get this. Here's I don't. Let me ask whether you want this example. This is a sort of applied example, third harmonic microscopy. Can somebody say skip it or do it on the chat, and I'll follow your advice. Oh, I'm not seeing anything. I think I'm going to skip it because, well, maybe not. Maybe I'll do it. So it turns out if you have an ultra short laser pulse intensely focused in a medium, you generate what's called a third harmonic electric field in the forward direction, and it's proportional to this integral. So I'm taking this simply from a textbook by Boyd. And it's along the axis of the beam. And here I'm saying B is this, and N is the index of refraction, and so forth. Lambda is the wavelength, T0 is a transverse radius, and so forth. The electric field looks something like this. And for normal dispersion, the index of refraction increases with increasing frequency. And so then delta K, which is defined as this, is negative. And since that's negative, this exponential is damped when you're in the lower half plane. And so we can add a contour and then go around the lower half plane. And what do we get? Well, this function f of z, which is the integrand here, is has a double pole in the upper half plane, but not in the lower half plane. So the integral is 0. So we don't get any signal at all. On the other hand, so the idea is when the dispersion is normal, the third harmonic signal vanishes as long as the medium with more or less constant chi3 of z effectively extends from minus infinity to plus infinity. So the edges are in the unfocused region, like there. On the other hand, if there's an edge with positive delta K in the focused region, then it does make a third harmonic signal. And so what you can do in what third harmonic microscopy does for you is it it makes you see edges and features instead of background. So now that I think about it, I think I should have skipped that example. So now let's look at evaluating this Fourier transform. It's a Fourier transform of 1 over k squared plus m squared. If x is positive, then the exponential decreases as you go up in the imaginary plane, because the k then acquires a positive imaginary part. The i's, you get I squared times something positive if x is positive. And so the farther you go up in the complex plane, in the upper half plane, the smaller the integrand. And so you can add r e to the I theta as a ghost contour in the upper half plane. And if you do that, then you can replace this integral with this contour integral. You can factorize k squared plus m squared like this. And now you see there's a pole at IM. And so you just pick up the pole at IM. Well, Cauchy's integral formula tells us that that is equal to 2 pi I times the integrand evaluated at IM. So the integrand evaluated at IM is, first of all, the denominator, you get IM plus IM, 2IM, sounds like Sam IM. And then e to the I kx is then e to the I IMX. So that's pi, canceling, get pi over m e to the minus mx for positive m. For negative x, we have the opposite thing, and then we set k equal to r e to the I theta and go in the lower half plane. And then we pick up the pole at minus IM, and that gives us this expression. We combine the two and we get that this integral is pi over m e to the minus m absolute value of x. And of course, here I'm assuming m is positive, so as not to clutter up the equation with absolute value signs. This formula allows one to write the Green's function of the Laplacian in cylindrical coordinates. And if we go back to the Coulomb Green's function, let me see if I can get this thing to show us. That's the Coulomb Green's function. If we then write r as rho squared plus z squared, so we're in cylindrical coordinates. Rho is the distance from the z-axis, and then z squared. We have this expression here, and the integral over the z component is then this expression here, kz squared plus k squared, the radial part. And that then turns into this, and we then have here an integral dk, which is severely damped, and a phi integral. The phi integral turns out to be a representation of the zeroth Bessel function, and as we'll see when we do Bessel functions. And so we get an expression for the Coulomb Green's function in terms of a Bessel function and an integral over a Bessel function. This is one of Schwinger's many formulas. Schwinger, by the way, was invited to join the Manhattan Project in the Second World War to come to Los Alamos, and Schwinger's reply, characteristically intelligent and humane, was, no, he'd rather do something that would hasten the end of the war in Europe. And so he worked on radar, and very much advanced the Allied effort in radar, improved radar enormously, and sure enough, no nuclear weapons were used in Europe, because all right, let me not go on a tangent there. Anyway, that was one of Schwinger's many, many contributions. He was remarkably good at this sort of mathematics and at fundamental physics. He advanced quantum electrodynamics. Anyway, all right, let me not go on and on about that. So let's look at another example of a ghost contour. We saw that the Green's function for the Yukawa's differential operator is this. If we then let k dot x equal to kr cos theta, theta being the angle between k and x, we get this expression here after doing the cosine integral, the theta integral. And now we can add a ghost contour that loops over the upper half plane, r being positive, and bingo, we get the answer, which is the Yukawa potential, e to the minus mr over 4 pi r. Originally, people thought that the mu meson, which was seen in cosmic rays, was the Yukawa particle, but it then turned out that mu meson interacts electromagnetically and weakly, but not strongly, and so it was actually the pion that is relevant here, and the mass of the pion is somewhat heavier than the mass of the muon. Muon is about 105 MeV. The mass of the pion is 140. Of course, when I say the mass of the pion, I mean mc squared is such and such. How about the Green's function for the Laplacian in n dimensions? Well, the Green's function for the Laplacian in n dimensions is going to be an expression like this. It's the same in any number of dimensions. It's just that you divide by 2 pi to the n, and you have n k integrations from minus infinity to plus infinity, and you have an n-dimensional dot product, and k is a square of an n-dimensional vector. But now 1 over k squared we can write this way, and once again, to make progress, we have to first make things more complicated. And then we complete the square in the exponent. So we write minus lambda k squared plus I k dot x. We write that as a complete square and then cancel the error term. We then set alpha equal to this term that showed up, x squared over 4 lambda. And what we get then is d lambda, the dnk, and e to the minus x squared over 4 lambda, and then this integration here. We've completed the square, but of course this is this k integral is now independent of x, so we can drop the x term from there, and we just get this. And the k integrals are very simple. It's just that same k integral that I derived by means of the trick. And so that gives us 1 over 4 pi lambda to the n over 2. And now we do a change of variables, and we let alpha be x squared over 4 lambda, and that gives us this complicated expression. But this is a gamma function, a particular gamma function, gamma of n over 2 minus 1. And then one can check that this is the correct Green's function, gives the correct Coulomb Green's function. But it also, if you consider n equals 4, so space-time as opposed to space, and this would be Euclidean space, in other words, just 4 spatial dimensions, you get 1 over 4 pi squared x squared. How about the Yukawa Green's function in n dimensions? Well, that satisfies this equation. And so we get this expression, and we can use the previous formula. Oh, I see it's a little hard to show what that previous formula was. Well, it's 158. In other words, we're using this expression to write it as a dnk, as a d lambda integral. In other words, we get the k squared plus m squared as that. Then we complete the square once again, and having completed the square, we then can do the k integrations, and must say, oh yeah, the k integrations are just e to the minus lambda k squared. So it's the same trick, that the same standard Gaussian integral that I worked out for you before. And then we have a d lambda. And to relate this to a Bessel function, we set lambda equal to this. Now this is a, how would you know to do that? I don't know. Anyway, you then do the integral, or you just massage the integral, and then that turns out to be a particular Bessel function called a modified Bessel function. Again, that's something we'll encounter later in the chapter on Bessel functions. Here's another Fourier transform. To do this integral, we can add ghost contours as in the previous example. But now the integrand has double poles. And so we have to use Cauchy's integral formula, not just the Cauchy's integral theorem. Anyway, and it's Cauchy's integral theorem for derivatives. Anyway, for positive x, we add a ghost contour in the upper half plane, and we have this expression after factorizing. And Cauchy's integral formula then tells us this is 2 pi I times the derivative of the integrand evaluated at k equals im. Maybe what I should do is just remind you what Cauchy's integral formula is. I'm not sure you know what it is, but let me show you. So it's basically, here's the simplest Cauchy's integral formula, but then if you differentiate that with respect to z0, what you find is that the Cauchy's integral formula for the first derivative is the function, but z prime minus z squared. And the second derivative, it's 2 over 2 pi I. Same integral, but z prime minus z cubed. Any contour going around the point z in a way such that the contour and everything inside it, inside the contour, lies in the domain of analyticity. And then the nth derivative, you get this expression here. So, all right, so that's what we use, and then we have to just evaluate this derivative at k equals im, and that gives us this expression. When x is negative, we put a ghost contour in the lower half plane, and putting the two together, then we see we have this and we have that. And so for x negative, minus x is positive. So this turns into an absolute value. And so that's our expression. The integral of a complex Gaussian, I think I'm going to skip this because this is a rather detailed example. And maybe I should just give you the answer. So let me give you the answer. The answer then is an integral e to the I a x squared minus 2I abx is the square root e to the minus I ab squared. Okay, and I'm going to skip this section also. And now I'm going to do this example. The inverse Laplace transform of 1 over s minus k. Well, our formula for the inverse Laplace transform is 4.153, and it is basically this. Here's the thing that we want to invert. We want to find out what function has this as its Laplace transform. And so we write this as not just f of s, but f of s plus iu, and we pick u to be sufficiently positive that this integral du is going to converge. Now, f of s is 1 over s minus k, so replacing s by s plus iu, we get this expression. And now, what is that? Well, that is an integral now up the, we can add a ghost contour that goes around the upper half plane. And we're integrating u along the real axis. I mean, since it's iu, we're effectively going up the imaginary axis, but as a u integral, it's along the real axis. Then we add a ghost contour that goes around the upper half plane. It picks up the pole at u equal to I s minus k. And so we have this integral, and that cancels the 2 pi I, gives us this, which is e to the kt. And in fact, you can see that that was one of our standard formulas, namely that e to the kt has as a Laplace transform 1 over s minus k. Okay, now I've run out of coffee. Let me get my coffee. I'll be right back. Read this in the meantime. Okay, back. So basically, functions are single valued, and they map every number into a unique number, assuming that that f is defined for z. And on the other hand, a one-to-one function is a function that maps only one z into each image point f of z. And so we love one-to-one functions because you can take a one-to-one function and simply define its inverse, because if there's only one z that gives you f of z, then for any f of z, the inverse function is z, and that's uniquely defined. You know, since I'm not using this because it somehow isn't behaving correctly, I can make this much bigger. I don't know how big you want it, but I might as well go to the limit. All right, I guess this is probably big enough. So for an important example is the exponential function. For real number, the exponential functions maps every real number into a positive real number, e to the x, and it has an inverse function log x that maps every positive number e to the x back into x. And this is, so we say that the exponential function and the log are one-to-one on real numbers. On the other hand, for complex numbers, it's not the case, because e to the z plus 2 pi ni is the same thing as e to the z, because e to the 2 pi ni is just n times going around the circle and going from 1 back to 1 n times. So the exponential function on the complex plane is many to 1. And in fact, it's infinitely many to 1. And so, so the exponential function has no inverse function on the complex numbers, and its would-be inverse function maps z to log e to the z, which is z plus 2 pi ni, which of course is not unique. And so in other words, if z is r e to the I theta, then the logarithms of z are log of r plus I theta plus I 2 pi n. And because e to the log r plus I theta plus I 2 pi n is r e to the I theta. In fact, I should have added an extra. So let me make a note to myself. I should have added an extra. An extra equation I should have had here, e to the I theta plus I 2 pi n, and then the r, which is r e to the I theta. Of course, typically people want one of the correct values of a logarithm rather than all of them. And there are two conventions for choosing what you mean by n. And they're both very common. And of course, there are infinitely many conventions, but the two most common are that you choose n equal to 0 when z is in the upper half plane. In the first convention, what you do is you choose an angle. You say z. You choose an angle theta that is 0 on the positive real axis, and then increases as z moves counterclockwise around the origin, until it points just below the positive real axis. In other words, all the way around, theta is almost 2 pi. So in this convention, though, the value of theta as you cross the positive real axis drops from 2 pi, almost 2 pi, to 0, or to slightly more than 0. And so there's a discontinuity of 2 pi on the positive real axis. This is called a cut. The second common convention is you put the cut on the negative real axis. So here, what you say is theta is defined in the same way when z is in the upper half plane, but in the lower half plane, as z moves clockwise from the positive real axis to just below the negative real axis, theta decreases from 0 to a little more than minus pi. And then as z moves clockwise and crosses the negative real axis, it jumps by 2 pi. It goes from minus pi to pi. And these two conventions agree in the upper half plane, but differ by 2 pi in the lower half plane. Sometimes it's convenient to place the cut on the imaginary axis, or a line that makes an arbitrary angle with the real axis. And the important thing is decide in each computation where you're going to put the cut and stay with that definition. Don't change the cut when you're in a particular computation. Now, you see the logarithm and the exponential function are used to define many of the functions of mathematics and physics. And the arbitrariness of the logarithm gets transferred down the line and makes a vast array of mathematical functions somewhat ambiguous or undefined. And so, for example, if we take here z is r e to the I theta, and we raise it to a power a, what do we get? Well, z to the a is e to the a log z. And what is log z? Well, log z is log of r, the distance of z from the origin, that's well defined, plus I theta, that's a convention, plus I 2 pi n, and another convention. And now if we multiply through by a, we get r to the a, e to the I a theta, which is z to the a, times e to the I 2 pi n a. So z to the a is not unique unless a is an integer. If a is an integer, then this thing is just 1. On the other hand, if a is not an integer, then this thing gives you a phase factor, and it's convention dependent. So, for example, square root of z. So this is e to the 1/2. A is 1/2. And we have log of r plus I theta plus I 2 pi n. So this expression here. So that's square root of r being positive, e to the I theta over 2, and then e to the I 2 pi n, but divided by 2. So e to the I n pi. But e to the I pi is just -1. So this is -1 to the n. So square root of z is -1 to the n, square root of r, e to the I theta over 2. And there we have, when we cross a cut, what happens is we're changing our value of n from one value to another, and we get a factor of -1. So that's the square root. The mth root is z to the 1 over m. So this is e to the log r plus I theta plus I 2 pi n divided by m. Okay. So this is the general form of the log of z being r e to the I theta. And working this out, we have the mth root of r, e to the I theta over m, and then this factor that's dependent upon the convention of what n is and where the cut is. And this changes then by plus or minus e to the 2 pi I over m whenever z crosses a cut. Now, to make matters worse and more confusing, we can say, well, how about letting a, this a, be a complex number, u plus iv? So then z to the a is e to the a log z. This is e to the u plus iv, and log z is log r plus I theta plus our convention 2 pi n times I. We multiply this out, we get the naive expression, and then a rather complicated thing, because it's e to the minus v plus iu times theta plus 2 pi n. And this changes by e to the 2 pi minus v plus iu when z crosses a cut. One example is I to the I. And, well, what's I? Well, you can regard I as e to the I pi over 2 plus I 2 pi nz. So I to the I is e to the I times this thing, and that's e to the minus pi over 2 minus 2 pi n. So here the change of convention takes something that looks manifestly imaginary, turns it into something that becomes bigger or smaller, and something that's intrinsically real rather than imaginary. Of course, we can define then, a sequence of nth root functions. The nth one is going to be e to the log r plus I theta plus 2 pi n over m. And you have to decide what you mean by theta. So there are two definitions here. What do you mean by theta and what do you mean by n? And they're, of course, related. We call these different functions, each labeled by an integer n, different branches of the mth root function. And we can merge all the branches into one multi-valued mth root by using a convention in which you, as you wind counterclockwise around the origin, you go from one branch to another and smoothly. And so the idea is a sort of cylindrical staircase. And this was Riemann's picture. I think it's useful to look at this example of explicit square roots. So we have the square root of z. Are we going to put the cut on the negative real axis, positive real axis, or somewhere else? Well, let's just stick with negative or positive real axis. If we put the cut on the negative real axis, then basically as z goes up around the positive, the upper half plane, theta increases to pi, and then if you go down into the lower half plane, theta goes from 0 to negative values, eventually reaching minus pi. So for this definition of the square root, the square root function is then this expression here. It's the square root of r plus x over 2 plus I sine of y times the square root of r minus x over 2. And sine of y is y over absolute value of y. On the other hand, if we put the cut on the positive real axis, so then theta goes from 0 to 2 pi and then drops down to 0 again when you cross the positive real axis, then an explicit formula is, it has the same square roots, but the difference is that we multiply the first one by the sine of y and the second just by I. Cuts, of course, are discontinuities. People place them where they do the least harm. For the function z squared minus 1, which of course we could factorize, there are two common conventions. We can put the cut in the definition of the angle theta along the positive or negative real axis. And there's a sign discontinuity of minus 1 as you go from the sign discontinuity from square root of z minus 1 cancels the one from z plus 1, except in between minus 1 and plus 1. So the function then has a cut only from minus 1 to plus 1 in the z plane. So that's one choice that people make. If we used one of the common conventions to define this function, we'd have two semi-infinite cuts. If instead we put the theta cut on the positive or negative imaginary axis, then we just have a single cut running from minus I to I. So there are these different possibilities. Suppose we want to evaluate this integral, 0 to infinity dx over the square of x plus a times the square root of x, a being positive. Okay. We're going to put the cut on the positive real axis. So now we have an integral. Well, we're going to define something. An integral backwards along and just below the positive real axis. So we've got, this is a case where I really, really would like to be able to use this iPad, but I just do not see how to do that with so let me oh God. Oh Lord, now I've lost everything. Oh God. All right, that was a mistake trying to. All right, so what we're doing is we're defining here an integral that where we're integrating dx from infinity to 0, but the z is just below the real axis. So z is x minus I epsilon. And we flip the direction of the integral, or rather we say, well, this integral is minus that integral, because here we're above the real axis, and so the square root has a minus sign in it. And we can then take the limit z going to infinity of z over, basically saying that we can add a ghost contour. And so what we're going to do is we're going to integrate f of z along this contour from 0 to pi, and from pi to 2 pi. Those contours are ghost contours, and we then are going to add a pair of canceling integrals along the negative real axis up to the pole at z equals minus a, and then add a counterclockwise loop c around it. Well, this is all quite confusing. So let me show you the integral, these contours. We've got this, we've got one contour that we can integrate along here, along there, along there, along here, along there, around, out, down, and so forth. And ordinarily, if there weren't a cut discontinuity here, then the dot dash lines would cancel, and the dash line would cancel the solid line. But instead, we have to keep track of what is going on here. Now, the contour C is just a counterclockwise integral around the double pole. So C is just this, but it's clockwise, so we have a minus sign. So it's minus 2 pi I, the derivative of z to the a, respect to z at z equal to minus 1. And that we can figure out, that's equal to that. Now, the integral I minus, that's this integral, well, what is that? That is this integral here, and we have to figure out what x minus I epsilon raised to the 8th power is. Well, that's equal to this. It's just below the real axis. And so theta there is effectively 2 pi. And so then multiplying through, what we get is this. And then we see this is the same thing. This is minus e to the 2 pi ai times the integral I that we started with, which is this integral here. This is the integral I. The sum of all these is 0 because it encloses no singularity. So the thing that's 0 is, well, this is a ghost contour. These are ghost contours, so they vanish. But this integral that goes like this, it is 0 because it encloses no singularity. The singularity is outside, you see, it's outside. And so it is 0. And so adding these up together, what we have is I minus plus the C and the I plus. What we wind up with is I plus is just I, and then I minus is that, and then we add the integral around C. That's this. The other the others are ghost contours, and so we get as our answer pi a over sine of pi a. Well, that was somewhat of a mouthful. There's Euler's reflection formula. Maybe I should skip that. Here's another integral, dx over 1 plus x cubed, 0 to infinity. So this is a convergent integral, of course, and we let z be promote x to z, and we consider this function log of z over 1 plus z cubed. And then we consider, so f is log over that 1 plus c cubed. And then we do an integral along a ghost contour from as theta goes from epsilon to 2 pi minus epsilon, and along both sides of the real axis. And so then what we get is we pick up these poles, and we get this expression here essentially by Cauchy's integral formula or the residue theorem. And on the other hand, as we let I epsilon go to 0, log of x plus I epsilon is log of x, but log of x minus I epsilon is log of x plus 2 pi I. Here we put the cut on the positive real axis. And on the other hand, log epsilon goes to 0 as epsilon goes to 0. So the integral approach is minus 2 pi I times capital I as r goes to infinity. So in other words, we want to relate this to the integral that we started with, and the relationship is a factor of minus 2 pi I times the integral we want. And so we divide this by minus 2 pi I, and we get this expression here. Whoops, sorry about that. Well, of course, these integrals, and using various tricks of contour integration, adding ghost contours and so forth to evaluate various integrals, this can get arbitrarily subtle and complicated and messy. As we, I think, as you can appreciate from these examples, we are just about out of time, so I'm going to stop here. I'm happy though to tell you that conformal mapping is something that's it's sort of a new concept. Again, everything follows from just the definition of differentiability of an analytic function, but it's something quite nice that we'll get to next time, which is to say tomorrow at 5:30. So I'm gonna quit now, and I am going to try to figure out how to get this iPad to do what I want, because it's really helpful to